Hi everyone, welcome to the video. For those of you who don't know me, my name is Arda Kurtoğlu. I am a first year physics undergraduate student at the University of Oxford. This video is the first video of a new series on this channel. In this series, I will be discussing new maths and physics that I learned during my physics degree. And for the first video, we have something special relating to special relativity. We will be discussing Compton scattering. And as I said, I literally learned this a couple of months ago, so this is a way of revising new material for me, and I hope that you will also find it helpful as well. Anyways, without further ado, let's get into it. So, see you in the blackboard. Alright, let's see what this Compton scattering thing is all about. So, Compton scattering. I think this is best explained by drawing a drawing. So we will have a photon, okay, and its wavelength is lambda. This will be hitting a stationary electron, E minus. And obviously you could say, what do you mean a stationary electron? How do we get a stationary electron? Well, don't worry about that. Okay, this is the problem that we're dealing with. Okay, this is a bit different in reality, but like this is the easy case that we're treating, let's say. But this is still cool, I think. Anyway, so we have this electron, and then the photon will hit it. This is the initial case. And what about the final case? Well, it turns out, and this is one of the things that could happen, right? So the electron will be deflected, and the photon will be deflected as well, like that. And the thing is, since the electron is now moving, it wasn't moving initially, so the photon must have lost some of its energy. So it's going to have some other lambda as its wavelength, lambda prime. And I guess you could already see that we would expect lambda prime to be greater than lambda because the photon lost some energy, right? And this angle is theta. Our goal is to express lambda prime in terms of lambda, mass of the electron, theta, and, well, other constant, speed of light, for example, okay? So how do we do this? To do this, we will use a very powerful technique called four vectors. Four vectors. These vectors, so let me just construct one and it will make sense to you. So this is for the initial photon, okay? So I will denote it with a P, and I will say photon here, okay? So, well, actually, do I want to, let's do like that, this if you want. So I'm going to name this photon gamma, and this guy gamma prime. So I will say P gamma, okay? P gamma, and I put a mu here. This just says that it's a four vector that we're dealing with. This is going to have four components, as you might have guessed. The first component is the energy of the thing divided by the speed of light. This is by definition. So energy of the photon divided by c. All right? And then the second component is going to be the x component of the momentum. And since if I define it like this, x and y and z is coming out of the board, let's say, the momentum is only in the x direction usually, so I can just write p, the momentum, and the other components are zero because momentum in the y and the z are zero. So this is the four vector basically, okay? Nothing cool about it, but you will see why it's very cool in a couple of minutes hopefully. But this is just one guy, right? I also want to write the one for the electron. Well, so it's first of all going to be the energy of the electron. And please don't say, it's not moving, so it has no energy. Well, you could say that for a classical problem, but we're doing special relativity right now. And in that case, there's going to be the rest energy, which is mc squared, right? The famous equation, mc squared. But you divide by c, that's the definition. So mass of the electron times c. And it is stationary, so all the other components are zero. This is the initial case. What about the final case? Well, we will have the four momentum of the four vector of the other photon, right? Photon prime, gamma prime. So it's going to be Well, it will have some energy, E prime, let's say, over C. And the velocity, I mean the momentum in the X is going to be, let's say, well, it's momentum, let's say, P prime, let's call it, P prime times cosine of theta. Then there's going to be 1 in the Y, P prime sine of theta. And then it's going to be 0, right, for the Z. Now, I will make one simplification here. And it's that for a photon, and I'm not proving this, you gotta trust me. For a photon, the energy is equal to P times C. And you could derive this from Einstein's general energy formula, which is that E squared is equal to rest mass squared C to the fourth plus P squared C squared. So this reduces to E equals mc squared for a stationary thing. And if you say that the rest mass of the photon is 0, well, then you get that E is equal to Pc, okay? So using that, we could just factor out an E over C like so here, right? And we could do that here. If you do E prime over C, it's just 1 cosine of theta, sine of theta, and 0, right? And another cool thing is, this is what, well, we can get to this we'll talk about it later. Okay, anyways. So this is that. And, alright, so you could say, well, why don't you write the form momentum for the other electron? I mean, not the other electron, it's still the same electron, but it changed. It's doing something different, right? So it has a different force vector. But I'm not going to do it because we don't need to. And you'll see why. Now, the cool thing that I want to do now is to talk about the invariant. And I'm not going to talk much about it, but you will see that, I mean, this is just the momentum, right? These are just the momenta. You could write it as, even though it's 0, you could write it as this. And the cool thing about it is, if you, so let's see how do we describe this. So the cool thing is, in general, if you have a 4 vector, which is like energy over C, and then you have the momentum, right? If you do something funny about it, that is, if you take the first guy and square it, and if you subtract, so this is going to be, by the way, some weird dot product, which is sometimes called Minkowski dot product. If you do this step, you will basically see E squared divided by C squared, and then you have P squared, right? What is this equal to? Look at this formula. It is, well, I need to think about it actually. It's, I think, m naught squared C squared, right? Which is a constant. This is called the invariant, and we're going to be using that idea, which is pretty cool actually, which will simplify it a lot, okay? And I know that, I mean, if you're seeing this for the first time, this must be very confusing, at least it was for me, so please write in the comment section if that is the case. But this is the way we will go about it. So we will basically use some conservation ideas, and that is, you know, the form momentum of the, so the additions of the 4 vectors before the collision equals the sum after the collision, which is just this. And it makes sense, I hope, because this is just, let's call this, I don't know, prime as well. I hope this one makes sense, because this is just conservation of momentum and energy. This is just conserving energy and momentum, because each component of the vectors will need to be equal to each other after we sum them, and the first component has to do with energy and the other components have to do with the momentum, so we're conserving both energy and the momentum. And now if I solve this for the form momentum that I didn't explicitly write, this guy, right, and that's not it, okay, so that guy is going to be minus, I think, yep. It's going to be that, and now if I square both sides, this is where the magic happens. Obviously it's not magic, but it looks like magic. So what happens is, we discussed this, right, about the invariant. If you square that guy, that's going to give you it's going to give you me squared c squared equals. Now we're going to square this guy, and how do you do it? Well, you would square, so if we treat these guys as together, let's say, you would have, okay, this is a bit of work, but it's alright. So square of that minus 2 times p, let me write it explicitly so that we don't make a mistake. And then plus p gamma prime, that guy squared, okay? And already notice that since we're doing first component squared minus all the rest guys squared, for the photon, if you look at it here, that's just zero, right? Because I mean for a photon it's like pretty easy for any photon, let's say. So for photon, since it's like E over C and now you have P, well, E over C is P. So if you square E over C and then you subtract P squared, that's just going to give you 0. And that's just referring to the fact that momentum, the photon has 0 rest mass. So this is 0, that's fine. And there will be other things that are 0 as well, so stay tuned for those. That's why I call it magic, guys. Anyways, so if we expand the parentheses now, so we're going to have this guy squared, which is going to give that plus 2p, okay, and dot product, right? Don't forget about that. Plus this guy squared minus 2 p gamma dot p, okay, minus 2 p gamma, okay, and okay, so these will simplify, that's cool, and this goes to 0, right? So far so good. And I mean, to simplify, right? Who doesn't like that? Alright, so in this case we have 0 is equal to, well, how do we take this Minkowski dot product? Let's look at the four vectors that we have, and I will also make one little adjustment, and that is, this is I think what Planck suggested to explain the what do they call it, the ultraviolet catastrophe or something like that. So he suggested that energy is equal to h times the frequency, which is, and h is Planck's constant, so it's just a number, it's just a constant, it has units, and frequency is just c over lambda. So for energy here, I'm going to be writing h times c over lambda, so we just get, let me even erase it. So c simplify, we have h over lambda basically. And here we will have h over lambda prime. You don't write h prime because, as I said, it's just a constant. H over lambda prime, okay? So we have that, and right, so we will basically look at these guys. That guy and, that guy and, oh, I forgot, sorry about that. And this guy. So you basically multiply the first components, and that's it. You don't square it this time because you're not multiplying it with itself, you're just multiplying 2 of them. And you will subtract the rest, but since this is a 0 and the others are 0, it just simplifies, cancels out. So you get me c h over lambda. So that's handled, and minus. So the first guy is still looking pretty much the same. Only difference is lambda prime. But you gotta be careful now because so let's be careful about this. So I will be, you don't know actually, because it's still 0, right? The other components, they don't matter anyways because of these zeros. Now we will need to be careful. So minus the 4 vectors of the 2 photons that we're now dealing with that, okay? So you first multiply the first corresponding elements, which is h squared lambda prime, and then you subtract, right? We are doing the funny looking dot product, the Minkowski product. And look at this. This one won't matter. We will only deal with this part. So we have this and this multiply with the factor in front, so h squared over lambda prime cosine of theta. And if I distribute the minus, we get this. Now h will simplify. Some of them will simplify actually. Alright? And at this point, if I, let's see, what would I do? If I multiply both sides by, lambda prime over, lambda prime over lambda, if I do that, so we will basically have, okay, so, sorry guys, so if I multiply both sides by lambda prime over lambda, basically, we will have 0 is equal to MEC lambda prime minus MEC lambda minus h, right? So I multiplied by, so times lambda prime plus h cosine of theta. And if we solve for lambda prime this time, it's going to be, let's do step by step if you want. So C plus h minus h cosine of theta. All right, so we get that lambda prime is equal to lambda plus h over mass of the electron times c, and then 1 minus cosine of theta. Okay? And here, this is a wavelength. It has the units of wavelength. It has the units, dimensions of length, and this is sometimes called the Compton wavelength. And I want to point out one thing. We said we would expect lambda prime to be greater than lambda because the electron was gaining some energy. That means the photon must lose some energy. And look at that. This is a plus. And 1 minus cosine of theta. Well, that's going to be positive, right? Cosine of theta can't be more than 1. So, well, there you go, basically. As we expect, the lambda prime is greater than lambda. And you could say, well, for example, if cosine of theta is minus 1, so if theta is 180 degrees, you would have the maximum lambda prime. And if cosine of theta is 0, so if theta is 0, so if it is not deflected, which, I don't know, might happen maybe, well, in that case, the lambda doesn't change at all. I don't think that's really physical though, yeah. Okay, so this is it for this video. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care.